Welcome everyone for today's NPTEL course, that is Environmental Chemistry, and this is the sixth live session. I am Saptarshi Bose here, a PMRF research scholar from IIT Madras. So welcome everyone to our NPTEL course of Environmental Chemistry. So the first question of our live session 6 is, a solution is titrated using NaOH and the change in pH is plotted against the volume of NaOH used. According to the plot given below, you can see it's clearly visible, the plot. So which of the pH points have good buffering capacity? This is our question, right? We have few options and multiple options can be correct. So think properly and give your answer in the chat section. I hope everyone will do it very quickly. So let's go for the solution. The answer is pH 4, 8 and 12. So this is the solution. So around pH 4 and 8 and 12, if we add base NaOH, the change in pH is very less. Thus, we can say this is the buffer point, right? So basically, pH 4, you can see like 4 will be something like that. pH 4, right? 4, this is the place, area. And another one is around this, uh, a, around this region, right? And another one is this region, right? So you can see that we are increasing the NaOH volume, right? We are increasing the added NaOH volume. We are pouring NaOH solution, and you can see here the with respect to the change of the volume. So it was something around 8 ml, then it's something around 28 ml, right? Within this range, there is not much vertical increment, right? So that's why pH is almost same. It's just slightly varying. But here you can see pH is varying rapidly, this point, right? So this is our first buffer point. So you know what is the concept behind the buffer point. At the buffer point, if you add base or acid, the change of pH will be very low, right? Those are the points where we can say that we have some good buffer capacity, right? Another one is like around this 8 pH. So here also not much vertical pH change. It's just going horizontally due to the addition of our NaOH solution and again at 12, right? Hope this is very much clear for everyone. We will go to the next question. So the next question is quite similar. The two solutions, solution 1 and 2, are titrated by adding acid or base, right, into the solution. And the change in pH is plotted against the volume of acid or base added, right? So this is our plot. Which of the following options are true for the graph? These are our options. Whether this pH above 10, at pH above 10, solution 1 is a good buffer, then solution 2, then solution 1 has a good buffering capacity in region 1, and so on. So you have to check and answer quick. Okay, let's go for the solution, right? So the solution is something like that. So the first option is correct. At pH 10 above or at pH above 10, solution 1 is a good buffer than solution 2. Then solution 1 has a good buffering capacity in the region 1, quite similar. And then solution 1 has a good buffering capacity in region 3, right? So here you can see that in this, if you are dividing this a region 1, 2, this is the 2 region, and then there's a 3 region, 3 sections. If we just go on like that, then we can see that at pH above 10, solution 1 has a good buffering capacity. So in this region, it has a good buffering capacity, right? And here, not much good because this is almost horizontal, but this coming to as a vertical, right? It's just at the verge of the vertical movement, so it's not good. So right, it's a respective judgment. So or the relative judgment. So depending upon the solution 2, solution 1 has a good buffering capacity uh, in the range above this 10, and then also this range, if we took this only this much, it has a good buffering capacity here, and also in this range it has a good buffering capacity, because if we add base or acid, there is not much change here, right? There is not much change, but this place is not good, right? In terms of buffering capacity, this is all not good. Let's go to the next one. A buffer intensity versus pH graph is drawn for a multiprotic acid, right? And which of the following options are true for the graph shown below? So this is the graph, the buffer intensity versus pH graph, right? Buffer intensity versus pH graph. And also one more thing, it's a multiprotic acid. So all of you know what is multiprotic acid, or is diprotic, triprotic, multiprotic, like, or monoprotic acid. So you can think about the examples, possible examples of a monoprotic and diprotic, triprotic acids, and just answer this. Which of the following options are true? The graph is a diprotic acid, is for triprotic acid, pK2 value, pK2 value, something like that. Just a minute. Pardon. Sorry. Okay, let's go for the solution. So the correct answers are, the graph is for triprotic acid, pK2 value is 6.7, and number of high buffer intensity regions are except for extreme pH values, right? So here you can see that it's a triprotic acid. Okay, so why? Because this buffer intensity is high in these three regions, right? Three regions buffer intensity is high. So it's a triprotic acid. You know, by the definition, by the concept of buffer, buffer capacity. This is nothing but when there is suppose this is H2CO3, right? So when there is it's getting dissociated, right, as H plus ion and also HCO3 minus. So bicarbonate ion, right? Hydrogen ion and bicarbonate ion. So it is getting dissociated, right? So when there will be the equilibrium, right? There will be an equilibrium of this species, right? So there is equal amount of H2CO3 and HCO3 minus. So there can be a reverse order reaction, right? There can be reverse order reaction, right? So this is the forward reaction and backward reaction rate will be equal that time. So at that pH, at that point, that forward and backward reaction rate is same. That's why there is not much pH change. If you add base or acid, there will be not much pH change at that point. But if you just cross this equilibrium point, then again there will be some changes, right? So this is how it occurs. So from this graph also you can see, or this one, right? Yeah, this one is the correct one. So here in this position, so whatever the species, the forward and backward reaction is same. So whatever is getting produced, then it can go in the backward reaction or backward direction. Whatever is getting produced, it can come back to its original position. It can come back to H2CO3. So that is why there, if you just if you just add NaOH or any acid or base, there is not much pH change, right? But when you cross this point, when you add additional amount of acid and base, then you can overcome this point, and then new species can be formed, right? And the number of new species formed will be more than the original one. So it will be not easy to get back to the previous state, right? So that's why here we can see the pH change. Basically, it is taking up the H plus ions that time, right? So, or it is like something like that. It's taking H plus ions is recombining in this stage, right? So again, after some time, it will be changed, something like that, or it is giving up the H plus ions. Both way is possible. It can give up. Suppose there is a bicarbonate ion, it is giving up this H plus. Right? It can also give up this H plus and can form CO3 2 minus, right? CO3 2 minus or carbonate ion. So it can also give up like that. So at that point, we can find the buffer intensity as the highest. So we are getting this for triprotic acid, and also there was one correct answer like pK2. Yeah, this is almost like 6.7, right? 6.7. So this answer is correct. pKa2. Yeah, and this is also with pKa value. So pKa1, this is pKa2. I hope you can remember and correlate, right, with the previous studies, previous chapters where it was explained that what is pK1, what is pKa2, and how this is related to this buffer intensity, right? And this is this pK3. So we are getting 3 pKa as it is a triprotic acid. And also the number of high buffer intensity regions are 3 except for the extreme pH value. So extreme pH values, it might be 14 or it might be 1. It can be different in those pH. So we are not taking the extreme conditions. If you take only this much, then you are getting only 3, right? Buffer intensity regions. So let's go to the next question. So this is if H plus equals to 1 millimolar, OH minus equals to 0.001 millimolar, and bicarbonate equals to 0.1 millimolar, and also carbonate concentration equals to 0.1 milli equivalent per liter. then the alkalinity is, you have to write down the alkalinity, you have to calculate quickly and answer to your chart section. Okay, we will go for the solution. So the answer will be alkalinity equals to minus 0.699 milliequivalent per liter. So this is the process how we can solve. Basically, according to the theoretical definition of alkalinity, I hope everyone I have gone through the lectures and also the notes. So you can relate what is the definition of alkalinity, how we are getting this thing. I'll not explain, but I will briefly say that this alkalinity in equivalent per liter, that's the unit equals to OH minus ion, which anions which ions are capable of getting H plus ions, like OH minus ions we are getting, HCO3 minus we are getting, and also CO3 2 minus we are getting. So this can take up the H plus ions. So the total concentration of these species minus H plus ion concentration. Why we are doing this? Because some of them can be combined with H plus ions, right, in the form of bicarbonate or in the form of H2CO3, right? So if it is in this H2CO3 form, or if it is in the bicarbonate form, then we have to deduct that much of the species concentration, right? We have to reduce that much of the species concentration in our calculation. Just put a bracket here, it will be easier for you to understand. So suppose this is the total species concentration which can take up H plus ions, okay? So this will be basically alkalinity, but we are also reducing the portion of them which are already occupied by H plus ions, right? Which are in this form. So we are deducting, we are reducing them. So then we can get the what is the net quantity of alkalinity, what is the total net quantity of the alkalinity, right? So and all these concentrations are in molar quantity or millimolar quantity. So one of the interesting factor is this, that milli equivalent per liter, only this one carbonate ion concentration was given in milli equivalent per liter, but we know that milli equivalent per liter equals to millimole, right? So this is nothing but millimole, and you can check what is the calculation behind this. Please check. I will suggest everyone. I already discussed in the previous live sessions that how to convert the units. So it's very easy. So here we don't need to change anything, and we are getting minus 0.99 milliequivalent per liter. Yes, we can get alternative in negative. Right? So we'll move to the next question. So if the CO2 gas is bubbled in a solution, then which of the following options are true? Let's go for the solution. So the correct answers are: air calorimetry remains constant and EV pH decreases. So we will know how to solve this, right? First of all, this alkalinity I already discussed. This is the definition. And if we bubble CO2 gas in the solution, then what will happen? That H2CO3 increases, right? H2CO3 concentration will increase, and H2CO3 will dissociate into H plus and CO3 minus ions. So this is the equation, like CO2 gas is converting into H2CO3 aqueous solution, and this H2CO3 is dissociating into 2H plus and CO3 2 minus. So if the increase of H2CO3 aqueous is 1 equivalent per liter, suppose, then the increase, suppose this is increased at 1 equivalent per liter, then H plus will be increased 2 equivalent per liter, because this is the 2. From 1 H2CO3, I am getting 2 H plus ions, so it will be 2 equivalent per liter. But the increase of carbonate is 1 equivalent per liter. Only one is there, 1 equivalent per liter. Then that the increase in both the quantities, if you just put here, so if we increase this per 1, and this will be twice increment, and this will be the once increment. If we put the values here, right, here and here, it is multiplied by, already multiplied by 2, and this is multiplied by 1, so it will be cancelled out, right? Twice H plus, it will be 2 into 1, it will be 2 into 1. So the increment, whatever the increment is, will be the change, or better to say, the net change will be 0, because they will cancel out each other. Smooth the values. If we take increase this 1 by 1, it will be twice the increment, and it will be 1 increment, and is getting multiplied by 2. Then it will cancel out each other, and the net change will be 0. So thus the alkalinity remain the same. So this total alkalinity, there will be no change, because these are cancelling out each other, right? And then H plus ions will also increase, but the H plus ion concentration is increasing, right? It is getting dissociated into H plus. So as we know that pH equals to minus logarithm of H plus concentration, so the pH will decrease. So as the H plus ion will increase, and then pH will decrease, right? Then the next question number 6. If CO2 gas is bubbled in the solution such that the H2CO3 increases by 1 equivalent per liter in the solution, then which of the following options are true? They will go for the answers. So the correct answers will be B, C, and E. You can see the total acidity increases by 2 equivalent per liter. Phenolphthalein acidity increases by 1 equivalent per liter, and H plus increases by 2 equivalent per liter. So we will see how to solve this. That if we bubble CO2 gas in the solution, then H2CO3 will increase, right? And will dissociate into H plus ions and carbonate ions, right? This is the gaseous carbon dioxide. It is converted into H2CO3 aqueous. Then H2CO3 aqueous is getting dissociated with bicarbonate ion and H plus, and then again it can also form 2H plus ion and CO3 2 minus ions. So we know what is the total acidity. It is nothing but H plus, total H plus ion concentration, plus H2CO3. It will give 2 H plus ion. That's why we are writing 2, right? It will give only 1 H plus ion. That's why we are writing 1 HCO3 minus minus OH minus. So again the same thing what I told already you, what I told everyone already regarding this total alkalinity, right, in the previous question. there was something like minus H plus ions concentration. Here is OH minus ion concentration because it can take up the H plus ions and conform into the water molecules. That's why we are subtracting this total from this to get this total acidity. We are subtracting this H plus ion concentration, right? And then what we have to do that if we increase this H2CO3 one equivalent per liter, then according to this our equation number 2, what will happen that one H plus equivalent will increase, right? For H2CO3 here as per this equation, one H plus I will get. So if I increase one equivalent per liter, then I will get one equivalent per liter of H plus ions increment, right? Then, as per the equation number 4, if you go this equation number 4, that is total acidity, here, what will happen that H2CO3 minus and H plus is 1 equivalent per liter, right? So it will, which raises the total acidity by 2 equivalent per liter. If you just put the values here, you will find that the total increase is 2 equivalent per liter, right? So if we are increasing this H2CO3 1 equivalent per liter, we are getting H plus increment as 1 equivalent per liter, right? And also we can get this HCO3 increment as 1 equivalent per liter. So here is one increment, right, in this species and in this H plus one. So total 2 equivalent per liter will be the increment. Here one increment, here one increment. Total 2 equivalent per liter increment. And then this phenolphthalein acidity, this is the definition. By definition, you can see H plus plus H2CO3 CO3 minus OH minus ions and again minus CO3 carbonate ion concentration, right? So we have to go to this equation number 3. So if we increase one H2CO3, then what will happen? That increase of H plus ion will be 2 and the decrease of CO3 minus ion will be 1 equivalent per liter because it is taking up 1 carbonate ions, right, to form this H2CO3. So what will happen? This phenolphthalein acidity in which the decrease of CO3 minus will be here 1 and increase of H plus will be 2 equivalent per liter. So the net rise of phenolphthalein alkali acidity will be 1 equivalent per liter. So here 2 increment, and here 1 decrease, right? So the net, this is 2. So the net change of the phenolphthalein acidity will be 1 equivalent per liter. So we'll go to the next question. So H2CO3 concentration equals to 0.1 mole is added into the solution. It's a closed system. And the alkalinity of the solution after the equilibrium is achieved is A, B, C, or D. You have to answer, right? Okay, we'll go for the answer. So the correct answer is 1.487 into 10 to the power minus 10 equivalent per liter. So this problem should be solved by vMinTech software. All of you are already familiar with this software. is nothing new. So first, what is the data? So the first data is that H2CO3 concentration is 1 millimolar, right? This is the only data, and it is a closed system. So no interference or interaction of the atmospheric carbon dioxide, right, or other gases. So here the total H plus ion concentration will be 0.2 molar, right? So 1 molar, suppose 1 molar of H2CO3 will give 2 moles of H plus ions, right? Because this is H2, simply 1 mole of H2CO3 will give 2 moles of H plus ions, right? Then 0.1 mole of H2CO3 will give 0.2 mole of H plus ions, right? So the total H plus concentration is 0.2 mole, and then this carbonate ion concentration is 0.1 mole, because 1 mole of H2CO2 will give 1 mole of H2CO3 will give 1 mole of only one. It has carbonate ion, so 0.1 mole will give zero point 0.1 mole, right? So just you have to give the inputs, right? H plus ion equals to zero point 0.2 and CO3 2 minus is zero point 0.1 in millimolar concentration. Then run the beam intake. Then you will find this concentration here, right? So you have to take the concentrations which you need. So we need, you can go for some print to Excel sheet and calculate the alternative here. So we know what is the alternative definition. That is nothing but OH minus ion plus bicarbonate ion plus twice into carbonate ion minus H plus ion. I already told you this, discussed this in the previous question. So just take what is the carbonate ion concentration we have, 5.0159 into 10 to the power minus 11. Right? Just put the value here, nothing else. You just put the value in this equation. Then check what is the OH concentration. So OH minus concentration is 4.83 into 10 to the power 11. Right? Just put the value here and so on. Like you have to put the value of HCO3 minus ion and also this H plus ion. Just put the values here and calculate. You will find in terms of equivalence per liter, because it's in the form of molar. Sorry, not it's not millimolar. It's in form of molar. The molar solution, or you will get the small. We are taking this molar solution is equivalent to molar solution for our all the questions already which we have solved. For that we are um, taking this, and according to this, this molarity is equals to the equivalent per liter, right? So there is no need to change the units, right? I hope you got my point, right? So thus we can solve this question. So the next question is almost similar with a small trick, that H2CO3 equals to zero point 0.1 mole is added into a solution and then it is kept in the flume. So it's an open system, not a closed system. And there's gas having HCO2, CO2 carbon dioxide, and H2S gas, hydrogen sulfide gas. And if the partial pressure of carbon dioxide is 10 to the power minus 2 atm and the partial pressure of hydrogen sulfide is 10 to the power minus 4 atm, then what is the alkalinity of the solution after the equilibrium is achieved? Okay, so we will go for the solution. The right answer will be 6.19 into 10 to the power minus 10 equivalent per liter. And this is how we will solve, right? So first, you know that I already discussed you that H plus will be zero point 0.2 mole, same data for the previous question and this question. So it will be zero point 0.2 mole, right? The H plus ion concentration, and CO3 2 minus concentration will be zero point 0.1 mole. Just write it down. The same thing you have done. Only the additional step you have to do to specify your gas. So just go to the specify gas option. You will specify the gas concentration. CO2 concentration is nothing but 10 to the power minus 2. So it is minus 1e minus 0.2. That's how you should write. You know, all of you know what is the um, symbol for 10 here. So we are writing this. Just write it down here. Just write it down here. The CO2 concentration, name of the gas is CO2, and then the pressure is nothing but 10 to the power minus 2. We are writing in this form. This 1 e minus 0.2. Just add this, right? And then go to the next one. Ah, that is nothing but, just a minute. Yeah, yeah, just nothing but for the second gas, this is H2S, and the concentration, the partial pressure was 10 to the power minus 4 atm. So just keep the input here, 10 to the power minus 4 atm, H2S gas. From the drop down, you will find the gas NEP, XCO2, H2S, something like that. Add it, right? And then you can also check is it correct or not. Yeah, you can check this is the correct one, that the log partial pressure is minus 2 minus 4 10 to the power minus 2 10 to the power minus 4 for CO2 and H2S respectively. Then just run the Vim intake. If you run the Vim intake, you will find the concentrations, right? Just like the previous one, write down your alkalinity here, right? And also one notable factor is that you have to, because here we are not having a closed system. So in case of closed system, this is your equation. But here we are not having closed system. We have H2S gas. That's why we are also adding the components from H2S gas, right? So this will also contribute in the total alkalinity, Hs minus and H2 minus. So it can take up H plus ions, right? It can take one H plus ion, it can take two H plus ions. That's why here one and here two. Simple thing. So it can take up two H plus ions. That's why I'm writing two. Here it can take only one H plus ion. Then it will from H2S. There will not no plus for any other elements, right? So just put the values from here, just like the previous one. Check what is OH minus. It is 8.17. Write it down here. Then go for HCO3 minus. It is 1.22. Write it down here. Just put the values in every uh, for every compounds and calculate. You will get calculated is 6.19 into 10 to the minus 10 equivalent per liter. I hope this is very much clear for everyone. So thank you everyone for joining today's session. We will end today's session now. Hope I'll meet everyone on the next Saturday at the same time. Thank you everyone for joining.